Okay, so let's move on. So the second part of chapter 21 is called charge is quantized. Okay, so we don't try to go very deep into this topic. Yeah, if it's that way, it is actually related to the quantum mechanics. Yeah, but actually we won't cover quantum mechanics in this course. So actually, charges quantized can be very simple. Okay, can be very simple. It can be like the electric charge is quantized, which means that the charge of a particle can be written as n times e, n times e. So here n is a positive or a negative number, and of course can be zero. So which has no charge. Okay, so it says positive or negative. And then E is so-called the elementary charge. Elementary charge. Okay, so which means the charge unit. Okay, the very fundamental unit of a charge element. Any positive or negative charge that can be deducted can be written as Q equals NE, where N is positive or negative integer. Positive or negative integer. So E is a well-known constant, which is 1.602 times 10 to negative 19 Coulomb. Okay, so usually what we use is E equals 1.6 times 10 to negative 19 Coulomb is sufficient. Okay, is sufficient. Of course, you have a calculator. You can just press the 1.602, but generally, we need 1.6 times 10 to minus 19 is accurate enough, in my opinion. Okay, so below is the table called, so we have three particles that you should have learned in high school chemistry, like inside an atom, we have electron, we have proton, we have neutron. Okay, so for the electron, it is usually denoted by E or E minus. Okay, with a charge amount of negative E. Okay, so it's a negative charge, and then for the proton, denoted as P. And it has a charge amount of plus E. Okay, so usually for an atom, it has the same number of electrons and protons. So an atom is by default a electrically neutral particle. And then of course it also has some neutron denoted as small n, and then it doesn't have any charge. Okay, it only have mass, but don't have any charge. Okay, so so charge is quantized. It's very simple. So here is it says when a physical quantity such as charge can have only discrete values rather than any values, we say that the quantity is quantized. It is possible, for example, to find a particle that has no charge at all, which means n equals 0, or a charge of plus 10e, negative 6e, but not a particle with a charge of say 3.57e. Okay, can't be a fractional number. Okay, so here we have a checkpoint. Okay, so here it says initially sphere A has a charge of negative 50e, negative 50e. Sphere B has a charge amount of plus 20e. The spheres are made of a conducting material, which means that it can have free electrons. The electron movement, okay, free to move within the material, okay, and are identical in size. So if the spheres then touch, what is the resulting charge on sphere A? Okay, So let's draw it out. So we have a sphere A. Okay, it has negative 50e, and then we have a sphere B. It has plus 20e. Okay, so we drag them and then touch each other. Of course, we don't try to add or pull out some electron from them from this system. Okay, so the total charge is like negative 50e plus 20e. So total amount of charge is negative 30e. Okay, so after contacting each other, and here we have another condition is that the two spheres are identical in size. Okay, which means that after the two spheres touch each other, the charge will be redistributed equally among the two spheres. So which means that if the sphere then touch, what is the resulting charge on the sphere A will be like negative 50e plus 20e. Okay, so this is the total amount of the charge in this system, and then half of this charge will go to sphere A, and the remaining goes to the sphere B. So divide by 2, which is negative 15e. Okay, so negative 15e on both sphere A. Okay, so any questions? Any questions? Okay, so it is quite straightforward. Okay, so here we have another sample problem. Okay, so here it says the nucleus or in an iron atom, okay, iron atom has a radius of about this, okay, this value, and contains 26 protons. 26 protons. What is the magnitude of the repulsive electrostatic force between two of the protons that are separated by this distance? Okay, so this is a very simple, okay, because we just need to use the Coulomb's force. So far, what we should have learned, the force between two objects is like we have gravitational force, which is attractive force, and then for the electrostatic force, it can be either attractive or repulsive, depending on the polarity of the charge. But here the case is like in an iron atom, okay, in the nucleus of an iron atom. Okay, so we consider two protons inside the nucleus. So both of them are positive charge, okay, positive E, okay. So they should be repelling each other. So this is the repulsive electrostatic force mentioned here. Okay, so actually F is like F equals K times E square over R square. Okay, so both of them are protons, so both of the charge elements are all positive E. Okay, so E square here, Q1, Q2 is E times E, which is E square. So we plug in the number 8.99 times 10 to the 9th, and then times 1.6 times 10 to minus 19 square, and then over this distance 4 times 10 to negative 15, okay, also square. So this value is 14 Newton, okay, 14 Newton, quite large value. Okay, so it is very straightforward. I don't stay too long here. Okay, so for question B, what is the magnitude of the gravitational force between those same two protons? Okay, so this is about the gravitational force, which is F equals G times mp square over the same R square. Okay, so I suppose you should have learned this gravitational force in the mechanics or in the physics one. Okay, so this is 6.67 times 10 to negative 11, and then times the mass of a proton is 1.67 times 10 to negative 27. Okay, so this is, and then the R is actually the same, 4 times 10 to negative 15 square. Okay, so the value is 1.2 times 10 to negative 35 Newton. Okay. Yeah. So you may think, so this sample problem is so stupid. What's the point of mentioning it here? Okay, so the idea is like, not all the sample problem in the textbook are trying to teach you how to doing the math. Okay, so actually this sample problem is telling you a physics story here. Okay, so the idea here is like, so the first question is, what is the repulsive force between the two between the two protons inside the nucleus? Okay, so you consider, okay, inside the nucleus there is a force repelling any two of the protons. Okay, the amount of the force between any two protons are not actually the same, because it only assumes the distance is the radius. Okay, so inside the nucleus it can be farther or closer. Okay, so but anyway, it is this is approximation, something like that. Okay, so as you have learned in the chemistry class, okay, so it should be a stable nucleus inside an atom. Okay, so as long as there are some force acting on let's say these two protons, okay, so there must be some force to attract them. Okay, otherwise there should be acceleration on the proton, right? Yeah, due to the Newton's second law of motions. So so here let us try to consider some attractive force. Okay, so one or maybe the only one attractive force we have learned should be the gravitational force, but the gravitational force is so small. Okay, so 1.2 times 10 to negative 35. Okay, it's much smaller than this one. Okay, so how come the nucleus can be stable? Okay, so actually the simple idea is that based on the knowledge we learn in the physics, we cannot really explain why the nucleus is stable there. Okay, so actually if you are interested in physics, okay, so there are something called the standard model of elementary particles. Okay, of course we don't try to go too deep or ask you in the exam, just let you know some of the physics stuff. Okay, so this standard model is like, so as long as you know, so we try to, so for the chemistry, okay, for the chemistry, what you learn is in the world we have different elements. Okay, so these on the periodic table. Okay, so in chemistry classes tell you, okay, so every element, okay, so the unit is called the atom. Okay, so every atom should be the same for the same element. And then inside an atom, okay, so we try to separate the atom. Okay, so we have an electron, we have a proton, we have neutron. Okay, so the further question is, for the physician, it asks whether we can further separate these kind of electron, proton, or neutron. Okay, so the answer is yes. The answer is yes. We have even smaller fundamental particle. Okay, so actually it's listed on this table. Okay, so actually something is called the quarks. The quarks. and something is called the leptons. Okay. If you don't like the English, you can also refer to the Chinese table. Okay, so something is called the quarks, a quarker. Okay, and then something is called the leptons, 亲子, quarks and leptons. Okay, and then also some other scalar boson and then gauge boson. Okay, so we don't care about that. So actually, if you use some method to really separate the proton or to separate the neutron, okay, it can have something called the up-down quarks. Okay, up-down quarks. Okay, so for the proton, it can be like for the proton, it can be like let me see. Charge. Okay, so it should be 2 up plus 1 down, plus 1 down. Okay, so you can see here. Okay, on the top left corner. Okay, on the top left corner. Okay, we have mass. Okay, charge, and then spin. Okay, so if you have 2 times of this, okay, this is 2 over 3, 2/3, 2/3, okay, 2/3, okay, times 2 is 4 over 3, okay, 4 over 3, and then plus this one, negative 1/3, okay, so it should be plus 1, okay, plus 1 charge, okay, of course in the unit of E, okay, so the charge amount is okay. But for the mass, okay, we just skip it. Okay, it is not written in the unit of kilogram. Okay, it's written in MeV over c square. Okay, you ask what is that? What is that? Okay, actually, in the particle physics, they usually like to use the unit of EV to represent the energy. Okay, the energy, and probably in primary school student may also know that E equals mc squared, although you didn't know how to use that. Okay, so actually E is the energy. Okay, mass is mass. Okay, and C is the speed of light. Okay, speed of light. So actually, they try to use the energy divided by c squared to represent the mass. Okay, to represent the mass. Okay, because if you try to change, if you are able to change some mass into energy, okay, so this is the relationship. This is the relationship. Okay, so but yeah, so just something like that. Okay, so actually, it's if it's a proton, it's like 2 up and 1 down, and if it is a neutron, okay, it will be 1 up plus 2 down. 1 up plus 2 down. So let's check the charge. 1 up is 2/3, and then 1 down is negative 1/3. Negative 1/3. Okay, multiplied by 2 is negative 2/3. 2/3 minus 2/3 is 0. Okay, so the charge amount is okay. Okay, so maybe you ask, okay, how about the others? Okay, so you can see there are some something called a generation. Okay, so generation 1, 2, 3. Yeah, so and then you can see don't necessarily need to go deep into the values, but at very least you can see 2.2 mega EV, okay, 1.28 giga EV, and then 170 giga EV. So the energy or the mass becomes larger and larger. So which means that you need more and more energy to really generate these so-called the higher generation elementary particle, like from generation 1 to generation 2 to so. Okay, maybe you will ask whether we have a generation 4. So far we cannot discover the 4th generation, but maybe if we can provide sufficient energy, then maybe generation 4 is possible. Yeah, because even though if we have this whole table, we cannot explain all the mass and energy inside the universe. Okay, if you have ever heard of the dark dark matter, dark energy. Okay, so actually all these elementary particles only represent less than 10%. Okay, or maybe I'm not very sure. About 5% of the observed mass in the universe. Okay, and even considering the dark energy is around 1/4. Okay, so more than 70% of the object, okay, in the universe, okay, cannot be represented by this standard model of elementary particles. Okay, so these are proton and neutron, and actually I can also tell you that, okay, for the electron, okay, the electron is not separable. Okay, so it is one of the elementary particles there. And okay, maybe other are too complicated, and then maybe this one you also know, the photon. Okay, photon, quants. Okay, so you probably should have learned it in high school physics. Yeah, because so the light can have some characteristic of a particle. Okay, even though it can also be a wave. Okay, so I don't try to go too deep into this one. Okay, because yeah, I'm not a physics expert. So just tell you some simple story there. Okay, so the last topic in this chapter is called charges conserved. Okay, charges conserved, which means that the charge cannot be created and cannot be diminished. Okay, it's just that easy. And then yeah, so here this formula is like we have a negative electron, and then we have also the positive electron, or sometimes we call it positron. Okay, if normal electron combined with another positron, okay, it becomes energy. Okay, so it's called the antimatter. Antimatter. Okay. Yeah. So a matter touched with its antimatter, they will vanish and then become some of the energy. Okay. So yeah. So become some gamma ray. Okay. Or maybe if there are large energy. Okay. Large energy may generate normal electron and also the positron. Okay, so actually in the Earth, okay, we can also have some positron. Okay, when there is light, it can also generate some positron. Okay, so charges concept is simple. Okay, it just means that the total charge amount inside a closed system cannot change at all. Okay, anyway, we try to talk about this so-called electromagnetic spectrum, or later in chapter 32 we call it the Maxwell rainbow. It doesn't really matter. Okay, so actually here it means that, yeah, so in this course we are trying to talk about a simple version of the electromagnetism. So yeah, and actually, of course, we are talking about the electromagnetic wave. So electromagnetic wave at the very beginning, people only know the visible light. Okay, because it is visible. Okay, other stuff are not visible. So in the past, they don't know. Okay, there are some electromagnetic waves that are not visible. Okay, so it is. So starting from the visible light here, and then also we have two axes. One is called the wavelength, and the other one is called the frequency. Okay, so in high school physics, possibly you have learned a formula like F equals F lambda, C equals F lambda. I mean, C is the speed of light. Okay, C is the speed of light. F is a frequency, and then lambda is the wavelength. Okay, so C inside the same material or inside the vacuum, inside the air should be a constant. Okay, this constant should be roughly around 2.998 times 10 to the 8th meter per second. Okay, C is roughly this value. Okay, so yeah, so which is a constant. Which is a constant. So which means that the frequency and the wavelength are inversely proportional to each other. Yeah, so you can see the wavelength. Okay, this side is very small. Okay, 10 to negative 12. 10 to negative 12. This is very long, and then this is very high frequency, and this is very low frequency. Okay, so so from the very left side, it can be something like the AM radio, FM radio. FM radio, maybe you seldom listen to the radio nowadays. And actually here we have the microwave effect, or actually the wireless, some of the wireless communication like the 3G, 4G or Wi-Fi actually using this frequency band around a few gigahertz. Okay, around a few gigahertz. Okay, like for the Wi-Fi actually use the 2.45 gigahertz, 5 gigahertz, something like that. Or maybe for the 3G, 4G, they may be using like hundreds of megahertz to up to 2 or 3 gigahertz, something like that. Okay, depending on the communication protocol. Okay, so yeah, so that is so-called the RF here, the radio frequency, the radio frequency. And then here is the infrared, infrared, 红外线, okay, and then the ultraviolet, 紫外线, okay. So, and then actually going up to here can be something, the X-ray, and then the gamma ray, okay, and then the gamma ray. And then, okay, so here is like a frequency, when it is going to the right side, become larger and larger. And maybe probably in high school physics, you may have also learned the E equals HF, okay, or H nu, okay, depending on the notation, okay. So H is the Planck constant. H is the Planck constant. Planck constant, and then F is also the frequency. So which means inside a photon, okay. So the energy of a photon is proportional to the frequency. So yeah, so we will say, okay, so the gamma ray is high energy, and then the X-ray is also high energy. So maybe when you try to enter the university, you need to check your lung whether lung is healthy or not. Then you use the X-ray, because the X-ray have a very short wavelength, so it will be able to penetrate your flesh. Okay, so that to check whether your lung is heavy or not. And then for the gamma ray, it's probably generated by the planet, okay, or by some of the planet outer world, okay, something like that, okay. Yeah, so here before we end this chapter, we have an additional example here. Okay, so here it says, yeah, so 3 identical conducting sphere. Initially have the following charges. Sphere A, 4Q, sphere B, negative 6Q. Okay, so let me write it down. Okay, this is 4Q, and then this is negative 6Q. And then for sphere C, 0. Okay, 0. Sphere A and B are fixed in place. Okay, they are fixed. Okay, they cannot move. And then with center to center separation that is much larger than the sphere. Okay, 2 experiments are conducted. In experiment 1, okay, sphere C touch sphere A and then separate and then to sphere B, and then it is removed, Okay, and then in experiment 2, starting with the same initial state, but it touch B first and then separate and then touch A later. Okay, then it is removed. And then it asks you what is the ratio of the electrostatic force between A and B at the end of the experiment 2 to that at the end of the experiment 1. Okay, so because the order of the charge exchanging is different. Okay, so the final charge amount on sphere A and B for experimental 1 and 2 are different. Okay, so they should have different electrostatic force. Okay, so it asks you the ratio. What is the ratio? Okay, so for experiment, let me write it like this. Okay, so we have ABC. And then for experiment 1, okay, at the beginning, 4Q, negative 6Q, and then 0 at the beginning, right? So at first, A and C touch each other. So for A and C, A is 4Q, C is 0. Okay, so the total charge amount are 4Q plus 0 is 4Q, and then equally separate to both of them. Okay, so it becomes 2Q and 2Q after the first touch. Okay, first contact, right? So B remains the same. Okay, because it is nothing to do with the sphere B. Okay, so the final step is touching B and C. Okay, touching B and C. So touching B and C will be like B is negative 6Q, C is 2Q. Okay, so total is negative 6Q plus 2Q is negative 4Q. Okay, so equally distributed to them will be negative 2Q, negative 2Q, and then 2Q for the sphere A, like this. Okay, so this is experiment 1. Okay, so we can see this is the final state. And then for experiment 2, okay, initially it's also 4Q, negative 6Q, and then 0. Okay, so this time we touch B and C first. Okay, B and C first. So touching B and C first, the total charge amount is negative 6Q plus 0 is negative 6Q. Okay, divided by 2 is negative 3Q. Negative 3Q, negative 3Q, and then A remains 4Q. So the last step is A and C touch each other. So A and C, A is 4Q, and then C is negative 3Q. So 4Q minus 3Q is Q. So divided by 2 is half of Q. Q over 2, Q over 2, and then negative 3Q for this one. Okay. Q over 2, like this. Yeah, like this. Okay, so this is the final state. Okay, so it asks you the ratio. Okay, so F2 over F1. Okay, will be like K times Q1, Q2. Okay, Q1, Q2 is actually this one and this one. Okay. Okay, so it asks you the force, the ratio of the force of experiment 2 to experiment 1. Okay, so we try to consider this one first. Okay, so this is this is Q over 2 times 3Q. Okay, yeah, because we only care about the magnitude here. Okay, we only care about the magnitude, so we just forgot the negative sign. Okay, actually over d square. Okay, actually finally the d square will be cancelled with the other one, so it is fine. Okay, so this one is 2Q times also 2q, and then d squared like this. Okay, so finally we can cancel this k and this k, this q, d squared. Okay, cancel most of the stuff. So this is 3/2, and then this is 4. So actually this is 3/8, or if you like, you can also write it as 0.375. Okay, like this. Okay, so this is another example before ending this one.